Good afternoon. We are on the third and final day of notes for 4.7. Today our focus is going to be on orthocenters and centroids, which are our other 2 points of concurrency. Let's start with orthocenter. The definition of orthocenter of a triangle. The orthocenter is the point at which the 3 altitudes intersect. And remember that an altitude is a segment from a vertex perpendicular to the opposite side. We talk about when we do an altitude, we say we drop an altitude because it drops straight down. Okay, looking at our 3 types of triangles, acute, right, and obtuse. Here are the altitudes. They're perpendicular, they do not bisect the angles, and they meet up in an acute triangle inside. Okay, so right here, that point there, that is the orthocenter, and it is inside the acute triangle. Now, on a right triangle, let's draw our perpendicular bisectors. Well, if you start at A and go perpendicular, it slides down the side of the triangle. That's perpendicular. C does the same thing. If you drop an altitude from C straight to the other side, it slides down the side of the triangle, right there. And they meet up in a 90-degree angle. Now, for the altitude to the hypotenuse, if you drop an altitude from B perpendicular to the opposite side, you can see that that line will meet up with the other 2 here at B. So this is the orthocenter of the triangle. And the orthocenter is on the 90-degree angle. So it's not inside the triangle, it's on the outside sitting at B, which is the 90 degrees. Okay, so finding the orthocenter of an obtuse triangle is a bit tricky, and we're going to construct it. I think the hardest part is we're tempted to drop it this way, which is good, but you have to realize on an obtuse triangle, the orthocenter is actually going to extend beyond A. So draw this line well beyond the triangle. Okay, so we're going to drop an altitude from C to the opposite side, but as you can see, the opposite side doesn't actually reach. So you're going to need to take the opposite side, which is AB, and draw an extension using dashes. And then when you drop your altitude, your perpendicular, it hits that side. Now you're looking for where the altitudes meet up. So extend that altitude on and boom, right there is your orthocenter. To confirm it, let's do the altitude from B to the opposite side. So again, your B to your opposite side, AC is too short. So we're going to need to take AC and extend it out using dashes. And then now do our perpendicular. There's our altitude. If you extend the altitude past the side, it hits the orthocenter. So on an obtuse triangle, the orthocenter, let's put an arrow right there, that is the orthocenter. The orthocenter is outside the obtuse angle. The obtuse angle is the largest one on the triangle. This is your obtuse angle. I'm going to use a pencil to just kind of color in this triangle a little bit so that you can see where the triangle is and where all the extensions are. So the orthocenter, where the altitudes meet up, is outside the biggest angle, right out there. Okay, so we're going to do a centroid. So that's orthocenter. Now we're going to do centroid. Okay, the centroid of a triangle is the point at which the 3 medians of the triangle intersect. Now, just to remind you that a median is from the midpoint of a side to the opposite vertex. That's a median. So here this one's done for you. You've got a midpoint of a side to the opposite vertex, the midpoint of a side to the opposite vertex, and the midpoint of a side to the opposite vertex. Where they meet up is the centroid. So this is an acute triangle. And the centroid is inside. Centroid. All right, so on the right triangle here, I've already indicated the midpoints to save you a little time. So we're going to connect the midpoint of EG, so those two pieces are the same, to the opposite vertex, which is F. Same thing with EF. Here is the midpoint, so these two pieces are the same. Connect the midpoint to the opposite vertex, which is G, and now the largest side. There's the midpoint of the largest side connected to the opposite vertex. So where the three of these meet up, that is C, the centroid. Now this triangle is actually a right triangle, so color in the square. So on a right triangle, the centroid is also inside. Okay, third and last, we're going to do the obtuse triangle. Again, you have a midpoint here of the longest side. So this piece and this piece are the same. Connect the midpoint to the opposite vertex. That's the median. Now here, these two pieces are the same. Connect the midpoint to the opposite vertex. It's the median. And this side, there's the midpoint connected to the opposite vertex, which is E. All three of the medians meet up at point C, which is the centroid. And this triangle here is obtuse because it has an obtuse angle at F. And as you can see, the centroid is inside the triangle. So whether the triangle is acute, right, or obtuse, the centroid is always on the inside of the triangle, no matter what. All right, flip the page. All right, we're going to do a theorem that has to do with a centroid. Okay, here goes. If a triangle has a centroid, which is the intersection of the three medians, then the centroid divides the medians into thirds. This is a very powerful theorem. So the length, so looking at this triangle, the length from the vertex to the centroid, so from A to C, vertex to centroid, is, so AC, is 2/3 of the median length. So it's 2/3 of AM. The length from the centroid to the, and this should be midpoint, not median. Let's fix that. The distance from the centroid to the midpoint, which is here, is CM. It's 1/3 of the total median length, so 1/3 of A to M. So you've got a 1/3 piece there and a 2/3 piece there, and it's usually pretty obvious which one is the 2/3 and which one is the 1/3. Okay, so we're going to do a problem. Example, given point C is the centroid. D got cut off, there you go. If C to F is 4, so let's label that, then what's A to C? Okay, so if this is 1/3 and this is 2/3, it means the big piece is twice as big. So it's really easy to calculate AC, because if you take 2 times CF, which is 4, you get your 8. So AC equals 8. So if you have the small piece, which is 1/3, and you multiply it by 2, you get the big piece. Okay, number 2. If BG equals 9, so they're saying the entire length of the median is 9, then what are the pieces? Okay, so the little piece is 1/3 of 9. So C to G is 1/3 of 9, which is 3. And BC is 2/3 of 9, which is 18 divided by 3, or a 6. So 2/3 and 1/3 of the total length. It's pretty straightforward. All right, let's do another example. It says P is the centroid of ABC. Okay, so centroid means that it's made up of medians. Medians connect a midpoint to a vertex. So right away, we can say that these two lengths are the same. We can say that these two lengths are the same. We can say that these two lengths are the same because medians make a centroid. Okay, so centroid, so P is the centroid of ABC. J to C is 12. Okay, let's label this. J to C is 12. B to P is 10. And BJ is perpendicular to AC. So BJ is perpendicular to AC. So BJ is perpendicular and it cuts it in half, which we can conclude then that BJ is the perpendicular bisector of AC. We don't know if we're going to use that or not, but it's helpful information. Okay, question number A, find the length of P to J. So here's our median. If this is 2/3 and this is 1/3, I can take B to P and divide it in half to get PJ. So we're going to take 10 times a half, and that equals 5 for PJ. I'm going to label that 5. There we go. Okay, find the length of B to J. Okay, so B to J then is 10 plus 5, which is 15. All right. C, find the length of AP. Okay, here's AP. We don't know anything about AI or PI, so we can't use our centroid theorem for this one. It doesn't work. What we do know, though, is that A to P is a part of a right triangle. And we know that BJ bisects AC. So if this is 12, this is 12. So I actually have two of the three sides of a right triangle. So to find the length of AP, which is question C, we're going to come down here. We're going to use the Pythagorean theorem, which says leg squared plus leg squared, A squared plus B squared equals C squared. And in this case, C is the hypotenuse that we're trying to find. 12 and 5 are the legs because they're attached to the 90-degree angle. So let's fill those in. 5 squared plus 12 squared equals hypotenuse C squared. That's our equation. All right, always do your exponents first. 5 times 5 is 25. 12 times 12 is 144. Then you add, this is 169. Then you need to take a square root of both sides. I'm going to flip-flop this around. 2 C's, 1 comes out. Now 169 is 13 times 13. So 2 13s, 1 comes out, and that gives us the length of AP, which is 13. And I'm going to label that on the drawing because we might need that. This is 13. Okay, we're supposed to find the length of A to J. Well, we already established that that was congruent to J to C. So AJ is 12, and that doesn't require any work at all. Last one, find the length of AI. Okay, AI is this whole length. So in order to find AI, I need to find PI. PI is half of AP. So PI is 1/2 of 13, which is 13 halves. So to find A to I, Oh, there's your equation, if you're looking for your equation. So a to I is 13 plus pi, which is 13 halves. That's your equation. So we're going to multiply 13 by 2 over 2. That gives us AI equals 26 halves plus 13 halves. 26 plus 13 is 39 halves, and that is AI, 39 halves. So you can see that each piece of information we get, we mark. Read the directions carefully and mark that information on your drawing. And then as you're answering the questions, put those answers on the drawing because you're going to use them to find other answers. This is just like one of our problems on the homework. Okay, flip the page. Now we're going to take a little shortcut on the notes here. I don't want the notes to go too long, but we do need to learn this stuff. Okay, so this page is the concurrency of an equilateral triangle. Remember, equilateral means all the side lengths are the same. So equilateral triangles have equal side lengths. And we know that equilateral triangles are equiangular, which means all the angles are the same. So all of them are 60 degrees. And there were two different theorems that we had that established that early. So this is an equilateral triangle. Side lengths are 6 centimeters, so we've already done that. And state the type of segment that forms the following intersections. This is a bit of a memory activity. So the centroid is made of 3 medians. And remember, a median is from a vertex to the opposite midpoint. Circumcenter is made from 3 perpendicular bisectors. The incenter is made from 3 angle bisectors. And the orthocenter is made from 3 altitudes. Okay, so if we try to mark these on our drawing, let's say that we start with the centroid. And since this is 6 centimeters, we're going to shortcut this a bit, just estimate where the midpoint is. And if I draw the medians, so vertex to midpoint, vertex to midpoint, vertex to midpoint, there's my 3 medians. That's my centroid. Okay, circumcenter is the 3 perpendicular bisectors. Well, we already know these are the midpoints, so these 2 are the same. These 2 are the same. These 2 are the same. And if you measure the angle of the median, you go, hey, wait a second. That's 90 degrees. That is the perpendicular bisector, and you would be right. So the 3 perpendicular bisectors are actually the same exact lines. Let's go to incenter. If you were to measure these 2 angles, what you would find is the median actually split it into 30 and 30. So this median is also an angle bisector, which means this one is an angle bisector and this one is an angle bisector. So the incenter is the same point. Now I think you can judge the theme. The orthocenter is the 3 altitudes. Altitude starts at a vertex, drops straight down perpendicular, and what do you know? Straight down and perpendicular is the same exact line. So the conclusion is an equilateral, we'll just put a slash, and equiangular triangle has 1 point for all concurrencies. And the 1 point, of course, is right here in the middle. That is the incenter, the circumcenter, the centroid, and the orthocenter. All right, flip the page. Okay, our other special triangle is an isosceles. And just to review, An isosceles triangle has two equal side lengths. We call those the legs, and they are part of the definition of isosceles. And an isosceles triangle has two equal base angles. And that is the theorem. So the definition is from the sides. The theorem gives us the base angles. All right. So this one's kind of fun. Let's start with the orthocenter, which is the three altitudes where they meet up. So I'm going to go from B straight down perpendicular. That's an altitude. I'm going to go from C straight down perpendicular. And what do you know? Crosses that middle point. And then from A, we're going to draw the altitude straight down perpendicular. So the three altitudes meet up right here. So it makes this point the orthocenter. It's where the three altitudes meet up. Okay, now we're going to do the circumcenter, which is the three perpendicular bisectors. Well, if you take from the top angle down, what you'll measure is that this actually is the midpoint. So this length and that length are the same. To get the perpendicular bisector, you have to find the midpoint of AB. So we're not going to construct this. It's 8 centimeters, so halfway would be 4. So you can mark 4 there. And since this is isosceles, it should be 4 centimeters here as well. So that's the midpoint. And a perpendicular bisector bisects the side and goes perpendicular out into space, just like that. And we're going to do the perpendicular bisector just like that. And these two pieces are the same as these two pieces. So this point right here is our circumcenter. And again, this one already is the perpendicular bisector, so they all meet up at that point. Okay, we're going to do the incenter, which is the three angle bisectors. And again, we're going to estimate this a little bit just for the sake of keeping the drawing tidy. So the incenter is the angle bisectors, and so the angle bisector actually goes through the second dot from the bottom. So this angle and this angle are the same. If you do the same for A, what you notice is it goes through the exact same point. This angle and this angle are the same. So because this is isosceles, angle A and angle C are the same angle. So these four pieces will be the same. This bisects the top angle. It's not the same as the other two, so I'm going to put a mark on it. There you go. And the three of those meet up right there. So that is our incenter. And there's only one dot left, so you probably can figure out where the centroid is. The centroid is where the three medians meet up. If I draw C to the midpoint of AB, which is we already have marked. If I draw A to the midpoint of BC, which we already have marked. And from B to the midpoint of AC is already there. So those three land right here. And that dot right there is the centroid. So all 4 points of concurrency are on the perpendicular bisector that goes from the apex angle. So let's write in our conclusions. An isosceles triangle has all points of concurrency on, and we can say the perpendicular bisector on the perpendicular bisector of side AC, the base. You could also say that all of them are on the angle bisector. So all the points of concurrency are on the angle bisector of apex angle A. Something you're going to need to know for your homework later is because B to this line is perpendicular, every one of these constructions form right triangles with the base of the triangle. So you want to write that in, that the points of concurrency make right, sorry, that's supposed to be a CY, make right triangles with base AC. So you've got a lot of different places where you can use Pythagorean theorem because that gives you the sides of right triangles. All right, we are on the last section of notes. Inscribing and circumscribing. Okay, so here we go. Theorem. Given a triangle with a circumcenter, and remember that your circumcenter are your perpendicular bisectors, and we say circumscribed in a circle. Now, when you say circumscribed in a circle, it means that the triangle is inside the circle, and B, A, and E touch the edges of the circle. So if you have that, then here's what's true. The circumcenter is also the center of the circle, and the radius of the circle is the distance from the circumcenter to any vertex. Okay, so here's our if the triangle is inscribed in the circle, then I can take and draw lines from C to each of the vertices, and no matter which vertex I pick, that's going to be the radius of the circle. So in our then grouping here, we have the circumcenter is the center of the circle. So C is also the center of, and remember how you say circle C, like that. C is also the center of circle C. And because these are radii, B to C is equal to E to C is equal to A to C is equal to the radius, which will be something you'll need to know. All right, that's our first theorem. Now our very last theorem. Given a triangle with an incenter, and if you remember, the incenter is made from the angle bisectors. So here is the incenter, and it has an inscribed circle. So it has an inscribed circle. When you say an inscribed circle, it means the circle is inside and it actually touches the triangle in 3 places. That's what inscribed in. So let's really quick, because that language, it can be challenging for people. So let's go up to the top here. If you say something is inscribed in, it means it's inside it. If you say it is circumscribed about something, it is outside it. So it's either inscribed in or it's circumscribed about. Those two terms are opposites of each other. So I can say the circle is inscribed in the triangle, I can also say the triangle is circumscribed about the circle. So that's how you can describe what you're looking at. Okay, so what do we know about this? This is the incenter. The incenter is the center of the circle, okay? And the radius of the circle is the perpendicular distance from the incenter to any side. And this happens at 3 places. Okay, so let's look at our visual. Here's our if. If we have a circle inscribed in a triangle, then we can put up here, I is the center of the circle. And if I put perpendicular, because you know, point to a side is always perpendicular distance, you'll notice that the perpendicular distances look really similar. With this theorem, they are not just similar, they're actually the same. And not only are they the same, they are the radius of the circle. So I is the center of circle I, and we'll call this, we can give these names D, E, and F. We can say that ID equals IE equals IF equals the radius of circle I. And when I think of these, just think of the circle starting small and getting bigger, bigger, bigger until it can't get any more large. That's when you've got a circle that's actually inscribed. It's as big as it can possibly get, and it's still touching in 3 places. All right, that is the end of our notes. I hope it was helpful to you. Have a wonderful afternoon.